to Friday Happy Math Hour. My name is Ruben Carrizales. Normally, Mr. Albert Isazi is the one that gives the 1324 session, but I will be covering for him today. So please um, feel free to ask me any questions. Again, open your mic. I don't have access to the chat. I'll be using a PowerPoint presentation. So if anybody has a question, needs me to slow down, needs me to go over something, please don't hesitate to ask me. Okay, so let's go ahead and get started. So today's session for the Math 1324 and the NCBM 0320, we're going to go over some basic concepts of probability, what permutation and combinations mean. And those are useful because we'll be using those concepts for probability. All right. So, so these are the topics. A brief introduction to probability, are the basic concepts of probability. We'll go over the multiplication principle. It's also called the counting principle. And then we'll go through these types of, I guess, probability math operations, right? They're called permutations and combinations. So let's get started. So first, to do the introduction of probability, we need to know that when we are doing probability, um, there one of the processes called an experiment. Okay, so a random experiment is the process in which the person doing the experiment won't find the results until he performs it. Okay, so we don't know what the outcome is until we actually do the experiment. So this is what's called a random experiment. And then the second term that we need to get familiar with is this notion of sample space. Sample space is denoted by a big S, and the sample space is a set of possible outcomes that the random experiment can produce. So as an example, let's say that I wanted to flip a coin. Okay, so we know that a coin has two sides. It has a head and a tail. So its sample space, the possible outcomes that I can get, it's either a heads or a tail. So I have two possible outcomes. So my sample space for flipping a coin is either heads or tails. Let's say that I was rolling a die, okay, or a dice, right? A die, I think it's plural, but a dice. So let's say that I was gonna roll a dice, um, um, or no, actually that's correct, die. Um, a die has six sides, right? So and then they're numbered 1 through 6. So the sample space of if I were to do an experiment rolling a die, um, I have six possible outcomes: 1, 2, 3, 4, 5, and 6. Okay? So to find the sample space of an experiment, at times it's easier to draw a tree diagram. And let me show you what that means or how to do that. So let's do an example again, finding the sample space of flipping a coin twice. Okay. So first we're going to flip the coin twice. So what we're going to do is we have two outcomes when we flip it once. We can get a heads or we can get a tails. But that's after flipping the first try, right? But then when we flip it again, if we got a heads the first time, then when we flip it the second time, we can either get a heads again or we can get a tails. Now, if we got a tails, then we roll it the second time, we can either get a head or we can get a tail. Yes? So this process of doing the possible um, outcomes that we can get by our experiment, this is what's called a tree. Okay. So here, if I wanted to find out what are the outcomes, okay, by flipping a coin twice, I could have two heads. Both times I flipped it could have been heads, or I could have gotten a heads first and then a tail, or I could have had a tail first and then a head, or I could have gotten two tails, right? So these are my outcomes that I can get by doing this experiment, by flipping my coin twice. And what I used to look at all the possible outcomes, I used a tree. Okay. So this is called a tree diagram. So my sample space by flipping the coin twice is this: heads, 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 tails, tails, heads, and tails, tails. So we have four possible outcomes. Okay. All right. So an event. An event is an outcome or set of outcomes of a random experiment. Okay. So for instance, in the previous example, my event was flipping a coin twice. Okay? So an event is a subset of the sample space. So what does subset mean? Okay, so what that means, and I believe in 1324 you've covered already set theory. So I hope you're familiar with subsets. But um, and what that means is that when I if let's say that I flipped a coin, right? I could have gone as an example two heads, right? But that's a subset of my sample space. The two heads were part of my sample space, which I could have had two heads, a tails, and a head, or tails, tails. This is what subset means. So again, this is what I just went over. By flipping my coin, okay, one of the outcomes that I could have had was a heads tails, right? So the event E, okay, we generalized the event as E. We could have gone just a heads, which represents the outcome heads. Yes? Okay, so let's do a checkpoint. Suppose that a die is tossed, write the given events in set notation. So I again, um, if I recall correctly, you all covered sets and sets notation. So let's go through this. So we're looking at here, the number is showing less than 3. So remember, when we throw a die, die has 6 numbers, 1 through 6. So we're trying to find a number that is showing less than 3. So those are only two possibilities. Numbers less than 3 on a die is just 2 and 1, right? So this is to do our solution. Okay, the number showing that is less than 3. Get in set notation, we have 1, we can get 2, and that's it. Those are the two numbers that we can only get that are numbers less than 3. These are my outcome, right? How about B? The number is showing is 5. Well, there's only one number that is 5. So for instance, the only subset that I can get by doing this experiment is to get that number 5. Um, the number showing is 8. Well, the die has only numbers 1 through 6. So this is not possible. I will never get an 8. So this is what's called the null character. Um, it's like a little zero with a slanted slash through it. Okay, this is null, means that we're never gonna get an 8 because a die does not have a number 8 to include. Okay, and it wasn't part of my sample space, right? So and then D, the number showing is even. Oh, okay, so we're looking at the even numbers. So again, those even numbers would be just 2, 4, and 6. Yes. Right. Again, please, if you have any questions, please let me know, or if I need to slow down, um, please feel free to just unmute yourself and go ahead and ask me. Okay. All right. So now let's look at basic probability. Okay. So to do a basic probability, um, uh, you're going to see this formula. Okay. So we denote capital P probability of an event is equal to the event divided by its sample space. Now, before I get through it, I'm not sure exactly how Mr. Albert covers it, but what I want you to know is probability, if you can see the formula, is a fraction. Okay, probability is not as will never be a whole number unless it's uh, 1. Okay, so probability only lives between 0 and 1. These are fractions. So whenever you're doing homework and you're calculating your using the probability principle, you're calculating the probability, and you get a value greater than 1, we've done something wrong. Okay, because probabilities are only fractions and they live only between 0 and 1. Okay, so here again, to put this in words, this formula here, the definition of probability is the probability of an event that is a number indicated that it's the relative likelihood of the event. So let me see here what he has. Um, so before I get started, before I do some of the examples, let's explain this relative likelihood. Okay, so I'm telling you that probability only lives between 0, and 1. So what that means, the relative likelihood of something happening. And most of us that we all practically have smartphones, right? And in our smartphones, some of us have an application for the weather, right? So we will look at the weather, and then the weather says, oh, there is a probability or there's a percentage of 10% of rain today. So we know that 10% is close to zero. So that means that more than likely, or the likelihood of it raining today is not going to happen. But if we looked at our app phone and it said, there is a 90% chance of rain today, 90% chance is very, very close to one. Um, so what that means is that if there's 90%, that means that it's likelihood that it's going to rain, right? So it's again, it's the likelihood of an event happening, and the values are only between 0 and 1. So let's look at this checkpoint. Suppose a single fair dice is rolled with a sample space of 1, 2, 3, 4, 5, 6, because those are the only faces that the die have, right? It says give the probability of each of the following events, and we're going to use this formula. The probability of an event is equal to the event divided by its sample space. So if we look at the part A, the die shows an event even number. So we did this already. We found out how many elements are in a even number, and those are the 2, 4, and 6. So that's my event. So that's my numerator. The denominator is my sample space. My sample space is the 1, 2, 3, 4, 5, 6, which is 6. So the way we would write this for A, that it's an even number. Again, we have three elements, and we are going, and our sample space is 6. So the probability of this event is 3 over 6, which is 1/2. We have a 50% chance that when we roll a die, we'll get an even number, right? And hopefully the 1/2 makes sense, 50%, because out of 6 numbers, half of them are even, the other half are odd. So that's our percentage, right? And again, remember, probability are always fractions, okay? And um, they only live between 0 and 1. All right, so let's do B. Um, the die shows a number less than 10. Okay, well, we know that we're not going to get 9, 8, or 7, right? Because um, the highest number that we have is 6. So on this particular one, I think he threw it on there just so you could see that the possibilities that I can get a number less than 10 are all of them, because they're all less than 10. So the event would be 6. My sample space is 6. So the answer is 1. And I talked about 1, right? If a number is 1, that means it's going to happen. So for instance, if I roll a die, for sure, I'm going to get a number less than 10, because those are all my options. I can get 1, 2, 3, 4, 5, or 6. Any of those that appear, it doesn't matter which one, it's going to be less than 10. So remember, 1 means that it's going to happen. Now, if we get a probability, and I don't know if we have an example here that oh, no, actually, I was going to get ahead of myself. Let's look at example C. Okay, so C says the die shows is an 8. And we did this already, right? Does a die have the number 8? No, right? The die does not have a number 8. The highest number that die has is 6. So in my event, there's none of them. There's none of the elements that would be 8. So I have 0 elements. My sample space is not going to change. It's still 6, but my event, there isn't any. So when I use my definition of the probability, it's the event, my numerator is 0 divided by 6 is 0. So 0 means that it's not going to happen. So again, 0 means it's not going to happen. 1 means it will happen. And again, as is this example number 6, there is no 8 in the dice, so it's not going to happen. It will never happen. Okay, so these are great examples to see uh, the the answers that we can get in probability. Okay, all right. So let's look at some more examples. And in probability, we love to use a deck of cards to do probability. Now, I don't know if there's an example of deck of cards. And I usually, when I teach probability, I like to go over a deck of cards because I have some students that probably have never played cards before. Um, and they have never and they're not familiar with a deck of cards. But just really quick, a quick brief through since we have the examples here to prove. Let me just tell you that deck of playing cards, again, the most popular game that you can think of uh, with a deck of cards is either blackjack or poker. Okay, those are the two most common uh, games that you can play with a deck of cards. But a deck of cards has 52 cards. Okay, and the reason why we like it in probability because it has a lot of sub events that we can pick from it. So, for instance, from this 52 deck of cards, we can split it up in two. We can split it up into uh, um, 26 black cards and 26 red cards. Okay. Now we could also split it into what are called suits. Suits are these shapes that this card has, and the 52 card deck has four suits. They're called spades, diamonds, um, clovers, and I'm missing hearts. Oh, I was almost missing hearts. So those decks are four suits. So each suit has 13 cards. Okay. Now inside those suits, there are number cards. There are cards numbered from 2 to 10. We also have some face cards that are called Jack, Queens, and Kings. And then we also have an ace card that we like to think of it as the number one. But these are all these subsets that we can get from a deck of cards. Okay, so let's look at this. Find the probability of drawing a queen. So a queen is part of uh, my four suits. There's a queen of hearts, there's a queen of diamonds, there's a queen of spades, and then there's a queen of clovers. So there's four queens. So for my event for A, oh, great, he showed an example, right? So if you see here, I have four queens, and they're the ones that are Q. We don't see the face card because, again, it's just a copy here, but the Q refers to the queen, and it would be a picture of a queen. But if you see, we have two black queens and two red queens, so we have a total of four queens. So that's my event. Um, and again, oh, he did explain here. So here are what I just explained. We have the four suits: the clubs, spades, hearts, and diamonds. The clubs and spades are black. The hearts and diamonds are red. Okay. So there's 52 cards, 26 black cards, 26 red cards. Okay, the the three face cards are the Jack, Queen, and King. Here's a picture of the Queen, right? So if we're going to answer our problem, we have our sample space is 52, the total number of cards. Again, the Queen means that I have four queens. That's my event divided by my sample space. So we have 4 over 52, but we always want to simplify this, right? So this will simplify to 1 in 13, right? And I had told you, right? There's 13 cards in a suit. So the probability that I can get one of those queens is 1 out of 13, right? So all right, let's look at B, a diamond. All right, so a diamond, we have 13 diamonds, and it's not specific what type of diamond, so we can get either a face card or a number card, right? So my event for getting a diamond, there's 13 diamonds. I'm going to divide that over my sample space, which is 52 cards. I want to simplify that always. So 13 over 52 is 1/4. So out of four suits, the probability that I get a diamond is 1 out of 4, right? So hopefully with time you'll see this. But again, this is the reason why we like using a deck of cards. There's so many options that we can use. All right, let's look at C, a red card. Hopefully you'll figure out the answer without doing the math, but let's go ahead and go through the math. Okay. So we see that there's 26 red cards. Okay, so that's my event. My sample space is 52 cards. So the using the probability definition is the event over the sample space, which is 26 over 52, but this simplifies to 1/2, right? So hopefully you saw that the probability of me getting a red card, if there's only two colors, black or red, it's 50-50, right? It's a half that I can get a red card. Ooh, how about D? What's the probability that we get a face card or an ace? So this is very, very important. This terminology of the word or. And again, hopefully you've covered this already. Or remember this when we did set theory. Okay, so here when we have a face card or an ace, our event is 12. So why is this 12? Right? So we have four aces, right? And we have three face cards. So this is where our multiplication is going to come into place, our multiplication principle. So the sample space, or sorry, the event for a face card or an ace, it would be this 4 times 3, right? So 4 times 3 is 12. So that's my event. What's my sample space? My sample space is still 52. Oh, sorry. Um, so we need to add for the for the or again the ace my excuse me. So our probability is 16 over 52. We always want to simplify this, right? So we have 4 out of 13, right? And I always want to jump into the answers. All right, so let's look at some basic concept probability, and he has it labeled as this is from section 8.3. So let's look first at the addition rule for probability. So if we have in events E and F from a sample space of F, um, again, this should be review, okay? So we have a probability of an event with a union of an F. We want E and F. And I was talking about the terminology is always very, very important when we're dealing with these problems. So the and always refers to this operation in set theory, which is called union. And the definition of probability for a union of two events is you'll do the probability of the event plus the probability of the other event, and you're going to subtract what they share, the intersection of E and F, right? Because we don't want to have duplicates. So this is the formula for when we're doing the and or a union. So let's do this example. Okay, this is a cool one. This is again feels like we're in Vegas, right? We have a roulette wheel. So we have when playing an American roulette, the croupier or the attendant, I like the way he's using the proper terminology. Nice. Spins a marble that lands in one of the 38 slots. So what spins is this round thing, right? The circle, and you'll throw a marble in here, and the marble's gonna spin in here as well. And when the roulette wheel stops spinning, the marble's gonna land in one of these options. Okay, so the options that we have for the roulette wheel is that it's numbered from 1 through 36 with two additional slots. It has a 0 green and a double zero green, okay, that are painted green. Now, half of the remaining slots are colored red, half of them are black. In roulette, the slots labeled 00 are not considered as even or odd. Okay, so just something to keep in mind. So let's find the probability of a marble that will land on a red or even. So first, we need to find our sample space. So hopefully, uh, we can see that our sample space, if we have 36 slots, but we have two additional slots that are labeled as 0 and double zero. So we have a total of 38 little slots that our marble can land in. So first, um, let's look at the event, right? The event says that find the probability that marble will land on a red or even. Okay, so let's look first at the red. Okay, the red are all these 1, 3, 5, 7, 9, 12, so on and so forth. Let's look at now the event of them being even. So event of being even are these numbers. So I love what Mr. Isasi did right here. The ones in red are duplicates, right? These are the ones that we're gonna subtract. These are our intersection values. Okay. So when we're looking at our formula, again, the event of it being red and even or even, right, is PR plus PE minus the intersection, right? So here, um, let's look at this. We have total of 38 um, slots. red are 18, 18 are black, 18 are even, 18 are odd. Okay, so the intersection of red and even are 8. So we can count them, right? These are the ones in red. The ones that are duplicates are in red. So we have 12, 14, 16, 18, 4, 30, 32, 34, 36 are our other 4. These are 8. This is our intersection. So now we can do our probability. Okay, so again, keep in mind, we're always using our probability for events. So the probability of getting a red are 18 over 38 plus the probability of even, which are 18 over 38 minus the duplicates or the intersection of them, which are 8 over 38. And our answer is going to be 28 over 38. But again, we always want to simplify this. And we're going to get 14 over 19. So the probability of us, let me read the problem again, find the probability that the marble will land on a red or even is 14 over 19. Okay. All right. So let's look at another example. Suppose two fair dice are rolled. Find each of the given probabilities. A. The first die shows a 2 or the sum of the results 6 or 7. Let's look at this. Okay. So let's do the solution for part A. Okay. So we are going to be using this example again because we want the first die shows a 2 or the sum of the results is 6 or 7. Okay. So we have first, let's represent the first die shows a 2 as A, and we'll show that the sum of 6 or 7 will be the B part. Okay. So let's go ahead. Oh, he did a table. Nice. Okay. So these are my results of tossing two dice, right? I can get 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. That the first die is always 1. And then he does it again, where we can get a 2, and then the other ones will change. The other dice can get a 1, 2, and 3, so on and so forth, right? So this here, this um, rectangle here shows our sample space. These are all the possible events that can happen when I roll two die, right? So um, here, if we see this implicates event A, where the first die shows a 2. So that's the second row here. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. The first die always showed a 2. Okay. And then we want the B part is the sum of 6 or 7. So how can we get 6 or 7? Well, 1 plus 5 is 6, and 1 plus 6 is 7. We also have 2 plus 4 is 6, and 2 plus 5 is 7. Or we have 3 plus 3 is 6, and 3 plus 4 is 7. 4 plus 2 is 6, 4 plus 3 is 7, so on and so forth. So these are all our possibilities that we can get a 6 or a 7. And if you notice here, we're going to have two duplicates, right? The duplicates would be 2, 4, and 2, 5, right? So we'll keep that into consideration. That's our intersection. So let's go ahead and put these answers on here. So again, my sample space is 36. There's 36 outcomes that I can get from um, rolling two dice. Now, I think we're gonna get to it, but another way, instead of visually counting all these, we can use the counting principle to get this value. And I believe he has an example of that. All right, so let's go ahead and look at first my event A. The event that the first die is 2, there's 6 of them. So that's 6 over 36. That's going to be that probability, right? The event that the sum is 6 or 7, there's 11 events that I can have that probability. So let's go ahead and put everything together. The probability of getting just a 2 first is 6 over 36 plus the event of it being a sum of 6 or 7 is 11 over 36 minus the subtraction of the two duplicates. And again, the intersection of A and B are that 2, 4, and 2, 5, right? Which is these two here. So I love his animation. So this is 2. So we have 2 over 36. So when we do this, we're gonna get 6 plus 11 is 17. 17 minus 2 is 15, so that's 15 over 36. Okay, which simplifies to 5 over 12. Okay, so this is our probability. And then again, if I would put this in my calculator, this number is going to live within um, 0 and 1. Okay, always, whenever you're doing these probabilities, if you get an answer that is greater than 1, we've done something wrong. Okay, so always double check your work, make sure that your probability always lives between 0 and 1. Okay, let's look at B. The sum is 11, or the second die shows a 5. So I believe he used this grid again. Okay, so let's use a grid to show what we need to do. Again, we're using the same um, formula here. So let's represent A as the sum is 11. The B part, let's have it be, and we only have these two values that our sum is 11, 6 and 5 and 5 and 6. That's the only way that I can get 11. Let's represent, which is 2. Let's represent B as the second die being 5. We know that this answer is going to be 6 because is this whole row where our second value is always 5. So again, our event is 6 for the B. So let's go ahead and put everything together, and you see that we will have one intersection. The 6 plus 5 is our intersection. So let's go ahead and put it in the formula. Our intersection is 1, right? So let's go ahead. The probability of A is 2 over 36. There was 2 that gave me the sum of 11, plus the probability of B, which was 6 out of 36, minus the 1 that has the intersection, right? So when I do this, 2 plus 6 is 8, 8 minus 1 is 7. So the answer, so my answer is 7 over 36. Yes, and I can simplify that, right? Again, please, if you have any questions, I've heard some things on the chat. I don't know if it was something else, but if you have a question, just unmute yourself, okay, and ask me. All right, so let's look at these two formulas, and the first one can be very, very helpful. It can help save us a lot of time with math operations, and this is called the complement rule. So the complement rule is read like this: P not E. This little hyphen here, we read this as not. Or the way you want to think about it is the opposite of the event happening. For instance, if I give you an example how easy you, before I go over the definition, how easy you can um, know what a complement is. So for instance, if I told you, I looked at my phone app and it said there's a 10% chance of it raining today, and if I were to ask you, well, what's the probability that it's not going to rain? Well, you would know that if there's a 10% chance of it rating, then the probability of it not rating is the other total for the one. So that would be 90, right? So there'd be a 90% chance that it's not going to rain, right? But this is how you would do it. This is what's called the complement rule. And to do the complement rule, you do 1 minus the probability of the event, okay? So you can rewrite it as this as well. 1 minus the probability of the event not happening, okay? There's also something called odds. Okay, so for those of you who've gone to a casino somewhere, okay, you always know that odds at casinos are never in our favor. They're always in the house favor. Okay, but the way we calculate the favor to find out to see to show you that it's when we're in a casino, the probability of us winning is not in our favor. You can do it by math. Okay, now so to calculate um, the favor of an odds is this: the probability of the event divided by its complement. Okay, so this is how we will calculate the ratio of odds. So let's look at some observations here. Okay, um, for this odds. Okay, so here the way you can do this is the probability event is still the definition of the event divided by the sample space, and the probability of the complement follows the same suit. It's the probability of the complement divided by its sample space. Okay, so just keep this in mind. We're always using our basic formula for probability. All right. So again, Mr. Sassi, the math here to show you that it's still the same thing. It's the product of NE over the N prime, which is what they're giving us. Okay. All right. So he also has it labeled here. An example that comes directly from your homework, page 27. I mean, page 434, number 27, right? So it's a marble problem. We Most of my students dislike the marble problems, right? But if we understand the formula, we can do this. Okay. So let's see. A marble is drawn from a box containing 3 yellow, 4 white, 8 blue marbles. Find the odds in favor in drawing the given marble. A yellow marble. Okay. So let's go ahead and do this. Okay. So first, we need to know that we have 3 yellow, 4 white, 8 blue. Okay, odds in favor of drawing a yellow. Well, we have the yellow and not the yellow, right? This is the probability of the event happening and its complement. So here, the probability of getting yellow is 3, right? That's our event. There's 3 yellows, so we can get 3 events. The probability of not getting a yellow is the 4 and 8, right? So that's 12. But again, just to practice our complement rule, right? Here we know that there's 15 total, right? That's the probability of getting all of these. So the probability of not getting a 3, that would be 15 minus 3, which would be the 12, right? So this is how you can use the complement rule. But again, to do the odds in our favor of drawing a yellow is the probability of the event, which is 3 over its complement. So this is 1/4. This is the probability of getting a yellow marble. Um, so, so the way we write it for the odds, so we see that it's not a probability but it's odds. We like to write it like this, and the way we read it is 1 in 4 that we will get a yellow marble. So 1 in 4 chance. That's our favor that we can get a yellow marble. Let's do B. What are the odds of in favor of drawing a blue marble? Okay, we would do the same process. The probability of the event that we get a blue is divided by not blue. So we have 8 blue, and we have 3 plus 4, which is our 7, right? So 15 minus 8 is 7. So the probability or the favors of getting a blue is 8 out of 7. There is an 8 out of 7 that in our favor that we will get a blue marble. And this makes sense, right? That this fraction is this way because there are more blues than 3 or than yellow or white, correct? Okay. Now, I also want to mention something, okay? We're looking at odds here. This is not probability. So if I would divide 8 over 7, this gives me 1.1 blah blah blah. That's bigger than 1, but that's not what we're doing here. We're not doing a probability. We are doing an odds, okay? So keep that in mind, okay? All right, C, odds in favor in drawing a white. Okay, so again, um, this is the probability of getting a white divided by its complement, not white. So there are 4 white marbles, so that's our probability of the event, 4. And the not a white is 3 plus 8, which is the 11, right? So here, the odds, again, just so we know that we're not dealing with probability, that's why we also rewrite it in this format. It's a 4 in 11 chance that we can get a white marble. Okay. All right. So this was to practice our complements and our odds. Okay. So he has another example here where he lists the page numbers and numbers. So let's look at this example. It says data from a 2016 general social survey can allow us to estimate how many hours people who classify their work status as part-time or full-time actually worked in the last week. Use the following table to find the probabilities of the events. All right, so let's go through this, okay? So let's kind of um, dissect in order for us to get these answers, right? So first, we're going to be using our formula for probability, the event divided by our sample space. Hopefully you see that our sample space would be everybody that was surveyed, right? So our sample space is all of these, our total was 1,591. That is our sample space. All right, so let's look at 47, full-time workers, okay? So how many full-time workers do we have? Well, full-time workers are this value 1,271. So to find the probability of full-time workers is the probability of the event of full-time workers divided by our sample space, which is going to give us this value, 0.7989. And I'm assuming that probably your homework, whether it's on the computer or on the book, is telling you to round to 4 decimal places, okay? So let's go on. Um, let's do number 48, part-time workers. Okay, so this is the probability of the event of getting a part-time worker. So there are a total of 320 part-time workers. We're going to divide that by our sample space. That's our event divided by our sample space, which is the 1,591. And we're going to get an estimation of 0.2011 as our probability. And again, all these answers, now we're back to probability, should be between 0 and 1. Okay? All right, so let's do 49. Worked 50 hours or more. Okay, so here, 50 hours or more. So that means that they either worked 50 or more hours. So if we look here, there's a column here for 50 or more hours. So the total number of people that worked 50 hours or more is this number, 393, our total. That is our event. We're going to divide that by our sample space, and that's going to give us, again, the estimation of 0.2470. Okay, so these are very straightforward. I hope you see them, how easy they are. All right, number 50, worked from 0 to 19 hours. So we have a column of people who work from 0 to 19 hours, and it tells me that the total is 106. So that is my event, 106 divided by my sample space, which is going to give me 0.0666. And I believe that should have been a 0.0667 uh, if we were rounding to 4 decimal places, but I may be wrong. Uh, let's look at where are we at. Oh, so let's look at this one now. 51 part-time workers and someone who worked 40 hours or more. Okay, so the word to look at here is the and. Okay, so when we're doing this, it's the sum, like it's that first example that we did, right? Of I think it was um, an even and a face card, I believe. I don't remember. So here, so for the and, um, who worked 40 hour, who was a part-time worker. So if we look at our part-time worker, our part-time worker um, between 40 to 49 is 49. And again, because we have a table, we know exactly just the number that we want, right? This is the part-time. 40 to 49 is 49 from our table. And who worked 40 hours or more. So 40 hours or more, we're looking at um, here, the 21, right? So 50 or 21. So we're just going to add those two numbers, divide by our sample space. Again, we have 0.0440. Okay. Now, I don't know, this is 40 hours or more. I'm thinking we should have added 49 and 21, but again, we'll leave it like this. All right. So number 54, part-time worker or someone who worked 29 hours or less. Okay, so now the word that we have is or here. So the way we're gonna do the or is, again, this probably we have to take away the duplicate. Okay, so but it's easy with a table. So let's go ahead and do this. Okay, let's see what we have here. So part-time worker, we look at our part-time worker that is 320 people who are part-time worker. We're gonna add that to someone who worked less than who worked 20 hours or less. So here, 29 hours would be a um, the 129, um, and less than that is also the 106. So that's 29 hours or less. We're adding those two, but we gotta subtract the duplicates, right? So what are the duplicates? The duplicates for the part-timers is that 77 value from the 320, and we also wanna subtract the 87, the part-time workers that have worked from 20 to 29 hours, right? So that is our intersection. So when we do that, um, and he has it written here, okay, we have it like this. So we have our probability of 391 over 15, 1,591, which gives us a probability of 0.2458, okay? And I still have time, so I think I'm pretty good. So now let's look at 9.2, which is the multiplication principle, the permutations and combinations, okay? So the multiplication principle is to figure out how many choices we can have, okay? So the best way to see an example is look at this problem here. That's on page 477. How many different heating and cooling units are possible if a homeowner has three choices for the efficiency rating of the furnace, three options for the fan speed, and six options for the air condenser? Okay, so for us to determine the number of possibilities that an owner can select a heating and cooling unit, we're going to apply our multiplication principle. And we call it the multiplication principle because in order to get this answer, you're going to multiply all of our options that we have. So we have a choice for efficiency, we have a choice for fan speed, and we have a choice for the air condenser. So for efficiency, there's three choices. For fan speed, there's three. For air condenser, there's six. So the total possible is 3 times 3 times 6. Okay, so that is 54. So applying the multiplication principle is to find how many different ways we can have a choice, okay, which will lead to probability. All right, so these are 54 different units are possible. This is customers can select from 54 different possible um, heating and cooling units. Yes. All right. How about this one? The United States Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are no restrictions on the digits used? How many would be possible if the first number could not be a zero? Let's do this. Okay, so this is easy. Okay, so first we need to note that we live in a world that only has 10 digits, right? 0 through 9. With these 10 digits, we can count forever, right? Um, and if we are doing the zip code, I like to do it this way, where I'm showing the spaces that I can fill out. The zip codes only have 5 digits, so I only have 5 slots. Okay, so let's answer the first part. There's no restriction on the digits that we can use. So for instance, if there's no restriction for a 5-digit zip code, again, I can choose any of these 10 for the first one, 10 for the second one, 10 for the third one, 10 for the fourth one, and 10 for the fifth one. I can choose any of these 10. So the number of possibilities that I can select or have a 5-digit zip code is multiplying all these numbers together, which is 100,000 possible zip codes that I can have. Okay. But let's answer part two, that we have a restriction now. The first digit cannot be zero. We cannot select zero. So if we cannot select zero, that leaves us with only 9 options to choose for that first slot. So that's what we're going to put there. 9 for the first slot, but the rest have no more restrictions. So the rest can be 10, 10, 10, 10. So when we multiply all these together, we get 90,000. Okay, so this is how we would use our counting principle to get possible options or outcomes. Okay, let's look at this example. For many years, the state of California used three letters followed by three digits on its automobile license plates, right? So until we ran out of possibilities, but you'll check this out. So let's look at here. There's 26 letters in the alphabet. There's 10 digits to do numbers. So how many different license plates are possible with this arrangement? This is was before. Now we ran out of these spaces, believe it or not. That's why it's California no longer uses this type of option because we ran out of options because there's so many people in the world now driving cars. All right, let's look at this. So there's 6 slots to do a license plate. So the first 3 slots are designated for letters. So the first option could be a letter, and the last 3 options could be the digits or the numbers, right? So the first one could be 1 out of the 26, 1 out of 26, 1 out of 26 for the digits, the 10, the 10, the 10. So the total number of possible license plates I can have using the counting or the multiplication principle is just multiplying all these together, right? So this gives me 17,576,000. Believe it or not, we ran out of these, right? We no longer can use just this basic way of doing license plates because we ran out. So let's do B. When the state ran out of numbers, the order was reversed to 3 digits followed by 3 letters. How many license plates were then possible? So then they had to do a little reverse to get more possibilities. So they reversed the order. Then they said we can now have digits first. The first 3 slots are for digits, and then the last 3 are for letters. But what do you think this number is? What do you think the answer is? So it's 10 for the digits, 26 for the letters. It's going to be the same number, right? But now we have the total of these two. Now we have, um, what is it? Um, 24 or almost 25 million. All right, let's do 6. Several years ago, the number described in Part B were also used up. The state then issued plates with 1 letter followed by 3 digits and then 3 letters. How many new license plate numbers will be arranged? So we ran out of these two. So again, let's do this. So it says that the first one had to be a letter, then the next 3 had to be followed by the digits, and then the last 3 could be the letters. Okay, so again, if we do this, there's 26 for the letter, 10 for the digits, and then the letters again. So then this gives us a total of 456,976,000, right? So again, we improved, and then they've also changed it now where the first 2 are letters, but we're going to get into that. All right, um, so let's look at what a factorial is because this is going to help us to do the permutations and combinations. So factorial is this symbol here, the exclamation point is the factorial symbol, and we use it to do the number factorial. So here, this is the definition, but I think you'll better understand it when I see an example. The only thing that you need to always keep in mind that 0 factorial will always be 1. Okay, keep that in mind. 0 factorial is 1. Just like how we have the anything to the 0 exponent is always 1, and it applies the same concept here for factorials. Anything to the 0 power for a factorial is 1. All right, so let's evaluate. Let me show you how this works. The way I like to do it is just the way the formula has it here. 4 factorial means that I'm going to multiply 4 times all the numbers that preceded. It's 4 times 3 times 2 times 1. So 4 factorial, 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. Okay, so this is how you evaluate factorials. So 6 factorial. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720, excuse me. And then 1 factorial would just be 1 because it's just 1, and that's it. And then I don't know if he does this for this problem, but we want to evaluate 6 factorial. Now, let me see if he has a trick to do this. Oh, yes, I think he did it. Okay, so let's say that I wanted to evaluate 6 factorial. So I know that 6 factorial would be 6 factorial, just from our examples here, is 720, and 4 factorial is 24. Then I would have to do that division, 720 divided by 24. But look, we can also help ourselves out. What we can do is we can cancel like terms to make the math a lot easier. So we can cancel the ones, we can cancel the twos, we can cancel the threes, we can cancel the four. So that leaves us with the one in the denominator, and all we have left is on our numerator is 6 times 5, which is 30. I don't know about you, but I would like to multiply just two numbers instead of having to divide um, 720 divided by 24. Okay, so this is a good way by using the formula. What factorial represents is to cancel like terms. Okay, so which leads us to permutations. Okay, permutations is a way to order elements in order. Okay, so when we're dealing with permutations, the order always matters. That's what ordering means. Okay, we are interested in the way things are ordered. Okay, so for instance, if we have the letters A, B, C, okay, um, the order that these can come in is A, B, C, A, C, B, B, A, C, BCA, CAB, and CBA. These are all the different ways that we can order them, okay? But if the order matters, okay, um, ABC and CBA, even though they're the same letters, except just backwards, these are two different orders. But the best way to see permutations, I don't know if he has it, is like this. How many batting orders are possible for a 9-person baseball? Okay, if the order matters, can we want everyone to bat? We don't want to leave anybody not bat, right? So here there are nine possible choices for the first batter, 8 for the second, 7 for the third, and so on and so forth, right? So here, the possible choices that I can have a batter is 9, 8, 7, 6, 5, 4, 3, 2, 1. Again, and we multiply these values together is 362,880. But again, this is when our order matters, okay? So the permutation of the elements is a factorial, okay? And that's why we covered the factorial. All right, so there is a formula to do probability using permutation where the order matters, and he has it bold with exclamations. Oops, I have run out of time, so let me go through these really quick. Again, I think you got the concept just to show you um, that the order matters. You can do the probability, which was we've done, and just to do a little combination. Combination means that order does not matter. Okay, so again, I'm gonna go through the example. You're able to just keep in mind that on your Blackboard, you're able to record these sessions. So please feel free to get the complete, slow down, go over it. Thank you for joining me today. I wish you the luck. We have one more week to go, and before finals. So wish you the best of luck. Thank you for joining me.
Well, just some quick announcements before we leave. For us, um, for right now, we're gonna have the at 1 p.m. the student success topic, which is gonna be service learning. And as he said, next week is our last Happy Math Hour week, and we're gonna be having final exam reviews. That's it, and I hope everyone has a wonderful weekend.